Alright, let's start. Hey guys, so hope you're all started with your prep. Okay, so most of you guys had asked for pointers and memory allocation. So let's start with pointers first. Uh, I'm just gonna assume you have covered like basic variable declaration and stuff. Okay, okay. So let's start with how memory is organized in your computer, right? Let's say this is your memory, and then you just chunk into the little boxes, and then so on. Let's just ignore the rest for now. I'll just stop through it. So each of these boxes is one unit of memory, and generally each of these unit is going to be 8 bytes, right? So each of these units is going to be 8 bytes, and each of these units has a unique address. So just like a location in real life, each of these units of memory is going to have their own unique address. Say this one is called like 1000 or whatever, and then this would be 1001 and 1002 and so on, right? So that's just how memory is. It's just a chunk. It's just chunked into 8 bytes, and then each of those 8 byte chunks will have their own unique address. That is how your memory is structured, right? Now, what are pointers? Pointers are just numbers. If you take a pointer, let's take an example real quick. Let's say index is 5, right? And then if you take the pointer of turn off copilot, right? If we take the pointer of x and print it out, it's just this number. Pointers are generally represented with hexadecimal values. So you see a hexadecimal number. So this is just the address of our x here. All right. So that's basically what the pointer is. So we saw that memory is just this huge space that is chunked into 8 bytes, and each of those bytes has an address, and the pointer is just a number representing that address. All right. There's nothing special about that pointer in that regard. It's just a number like that. So there are different types of pointers, of course. For example, because the data type you take the pointer of uh, dictates how the pointer behaves. So we have an integer here, right? So we took the integer pointer. Let's say x pointer is equal to ampersand x. So this now contains the pointer of x. So the pointer behaves differently based on the data type which is contained in the location to which the pointer refers to, right? So what this basically means is, let's say our x is here. So x is 5. Let's say x is here at 1000. So the pointer is going to behave differently based on where this is, right? So for 5 specifically, it's just going to be a binary, right? And then this is 8 bytes. Okay, so we know that each chunk is 8 bytes, and sorry guys, I made a minor mistake here. It's going to be 8 bits, not bytes. I apologize. My handwriting is no bits, make that big. It's going to be 8 bits. Alright, so back to our example. We have 5, right? 5 in little endian, it's going to be just 5 here. So however many zeros, and then it's just going to be 1, 0, 4, 2, 1, and then however many zeros here. And then this is an integer. So an integer is 4 bytes on modern systems. I hope you all know that. So the rest of the 4 bytes are just going to be zeros, right? So each chunk is going to be 1 byte, 8 bits, and then the first chunk will have 5, and then the rest of them are just going to be zeros. So I said that a pointer is going to be referring to a specific variable or data, right? So here it's referring to 5, and here we've assumed it to be at the address 100, but there are four bytes here, right? But we are only picking the very first of those. That is a very important point, which is you have multiple addresses at which one piece of data can be broken into, right? If the data you have is longer than 1 byte, you're going to store it in multiple consecutive addresses, and the pointer to that data will refer to only the very first address there, and not all of them. That is one important point. Secondly, uh, okay, I hope this clears up what a pointer is, and that confusion is cleared up. Secondly, pointer math, pointer arithmetic. So you can uh, add to pointers or increment or decrement pointers. This incrementing and decrementing of pointers is also dependent on the data. So we saw here that an integer is taking up 4 bytes, right? So if you increment a pointer from 100, say if you increment this pointer by 1, it won't become 101. It will become 104 because this is 100, and then these three are 101, 2, 3, and then this is the next space in memory that is not a part of this whole data, right? So this integer is occupying 4 bytes, and then if you increment an integer pointer, it's going to go ahead and skip those 4 bytes and go to the next path in memory that is not referring to the current the same thing as what the current pointer is referring to, right? So that's pointer arithmetic. So for integer, it will skip ahead by 4 bytes. For void, it would skip ahead by 1 byte. And then for char by 1 byte. For long, it would skip ahead by 8 bytes, and so on, right? So let's just look at that real quick here. Okay. So if you see here, just look at the last digit of these two addresses. it says 914 and then 918. So it skipped ahead by 4 bytes because we are dealing with integers here, and integers are 4 bytes in length. So the pointer increases by however many spaces the data type it takes, right? If you change that to a long, it goes from 0 to 8. So it's skipping ahead 8 bytes because that's how much space the current pointer is taking. And then if you increment it by 1, it's going to skip ahead by 8 bytes because the current data type is a long. Now, say I'm saying this is a pointer to an integer, which it isn't, but I can say it is because C allows you to do that. Now what happens is it skips ahead by 4 bytes because as far as C is concerned, this pointer is a pointer to an integer. So it skips ahead by 4 bytes, even though the location there is actually a long there, which is 8 bytes. So yeah, pointer arithmetic completely dependent on the declaration or the type you cast it to. So here I have cast it to an pointer to an integer, even though it's actually a pointer to a long, and that's why it's getting added by 4 bytes. So that's how different types work with pointers. Uh, yeah, so that would be pointers. If anyone has any questions, just drop it in the chat. I'll quickly clear them before moving on. Okay, I'll assume there are no doubts. And the next major thing you guys asked about is memory allocation. All right. So memory allocation. So before we talk about how to do it, we'll ask why. Why do you want to do memory allocation? Why do you want to manually manage memory when you can just declare variables and it just takes care of it for you, right? So what happens is sometimes you don't know how much stuff you want to store. For example, let's take Python. In Python, lists are not of a specific length. You can grow them by appending or extending them, right? You can add elements to the list. There is no limit set on the list. C arrays are not like that. So you want to emulate that for whatever reason. There are many reasons you want to use a list without a fixed size, right? So that would require memory allocation because you don't know ahead of time how much memory you need. Therefore, you can't declare an array with so and so amount of memory because you don't know if that will be enough. So that's where memory allocation comes in. You can ask for how much memory you want, and then it will be done when the program runs instead of when it compiles, right? So memory allocation, this is the why of memory allocation. Uh, Without going too deep, there are two types of memory when your program is running. Stack and heap. The stack memory is going to contain all of the data your program uses, the variables you have declared in your program. Let's say like you say print something, those strings or numbers are going to be stored in the stack. And then your normal function calls are all just going to be on the stack. Because all of that, you know how much size is going to take up at compile time. You don't need to worry about, well, if this is not going to fit, because you know the size, you can make it fit. And then heap memory is what you deal with when you're talking about memory allocation, right? Heap is just unordered memory, it's just a heap of memory, right? So whenever you malloc or calloc or realloc, it's all just interacting with the heap. So this is tied into pointers again. So the way you ask for memory is you just say malloc, right? Why is this tiny? Okay, you do malloc. What does malloc give you? Malloc gives you a void pointer. right? Malloc gives you a void pointer. So what does this mean? When you call malloc, you're gonna say I need so and so amount of memory, and then it gives you back a void pointer. So that void pointer is going to be the first memory location out, and from there continuously how much ever memory you asked, it's going to be allocated. Say you ask for like 16 bytes of memory. 16 bytes starting at the location specified by this void pointer is going to be allocated to you, right? So uh, when you use malloc, you generally want to cast it into the type you're actually allocating into, right? So void, it just returns void because void is a placeholder for I don't know what type this is, or there is no type here. Because when you ask for memory, it's just memory. There is no type associated with it. So whenever you call malloc, you want to cast it into the respective types. Let's take a quick example here. Uh, let's say you want to ask the user how many integers you want to store, and then create an array based on that, right? So number of random number of elements, and then just do, let's say, int x num. Okay, sorry, and then you just do scanf %d, and then and just reading in how many numbers you want to get, and then you want to include standard library .h because that's where malloc lives. So now what you do is, so essentially we want an array of numbers of length num. So an array is just a pointer, kind of. I'll get to that. An array behaves like a pointer. Let's say int nums is going to be int asterisk num, uh, and then we want to malloc, and then we do size of int times num. So what are we saying here, right? So this part, this malloc call is where you say this is how much memory I want. So you're saying I want however much the size of integer is, which is going to be 32 bits or 4 bytes here, and then I want to multiply it by num times. So however many integers the user wants to store, I want to put that many numbers, right? And then this part, you're just casting it into a pointer to an integer. So there's that. Okay. So int I is equal to 0. I'm just creating a copy of that pointer for walking through it. I is going to be less than num, and then we're just going to increase I, right? Okay. Before we saw that if you add one to a pointer, it's just going to skip all this and then just go over here, right? So that's what we're going to use here. So we start at 0, and then we just say num plus sign, the whole dereferenced. So what does this mean? You say nums plus I. Initially I is 0. So it's just nums. So it's just the plain pointer itself. So say it was 100 like in this example, so it would just be this pointer, right? And then if it was 1, it's going to skip over all this and then go here to this part, right? So we're just going to say nums plus that. Now this gives us the nth element in a right. So now what can we do with this information? We want to scan in integers, num integers. So we want the pointer for scanners. That's just going to be nums plus I. This is the pointer to the nth element. So we can just do scanf or printf, enter element number, say percent %, and then okay, percent %, is fine. And then we're just going to scan and input. We are taking in an integer, and then that is going to be put into nums plus I, which is the pointer to the ith element. And now we can just walk over the array again, I plus plus, and then print, and we can just do I and nums of I. Alright, let's run this right. Let's say I want 3 elements. 1, 2, 3. There we go. And then what did I forget to do? Free it. So when you're done with using this memory, right, you always want to free it. If you don't free it, that's called a memory leak. You're done using some memory and then you forget to free it. That is some memory you are not using, but that is still allocated for as long as your program is running, right? That's called a memory leak, and that's bad. We don't want that. Secondly, you do not want to uh, lose this pointer to nums under any circumstances, because that is what you pass in to reallocations or free, right? So you don't want that to go out of scope. Say you're allocating in within some function, and then you don't want to like return some value within the function, and then you just lose track of this memory you allocated. Then you can't free it. So it will be just there until your program runs, right? So that's bad. So yeah. Uh, so we didn't know how many elements we wanted to take in. So we used dynamic memory allocation here to allocate for however many elements and then assign values to them, right? So this is how you use malloc. Any doubts so far? Okay, I'll take that as a no. And also, while we're on this topic, let's deal with arrays as well. Let's create a new arrays.c. Okay, let's just copy some stuff. Yeah. Okay, Let's take an array of 5 integers, which are, let's say, 1, 2, 3, 4, 5. Right. Now, we have this array. What does this actually mean? So, we are just going to have this, we just have this contiguous chunk of memory with 5 elements. That's 1, 2, 3, and then 4 and 5. Right. So this is going to be 1. Why is everything so tiny? 2. I'm just gonna write. Okay, where is it? Yeah, 3, 4, and 5. Right. So this is what your array looks like in memory. An array is also just a contiguous chunk of memory. You can see where I think you can see where I'm going with this. So the first element of an array, let's say it's at an address 1000. Right. So we are dealing with integers here. So it's going to be, this is going to be 1004, 4, and then 8, and then 12, and then 16. It's just going to be incrementing by 4 bytes each time because we're dealing with integers and integers take up 4 bytes, right? Now, let's see what I meant by arrays are just pointers, kind of. Let's print out the pointer to the first element of the array. And then let's print out a pointer. Let's print out the array itself actually. So what happens now? Wrong side. Oops, I forgot a new line there. Alright, we can see that the array itself and the very first element of the array reside at the same address. An array is just the pointer to the first element. Now, what happens if you increment it? Percentage array plus 1. What is that? What if we add 1 to the array? It is 4. Now what if you take the pointer to the first element? Let's put it here. The array itself is going to be the pointer to the first element, and then array plus 1 is going to be pointer to the second element, right? So in general, array of I is the same as array plus I dereferenced. So array plus I will give you the pointer to the ith element in the array, and then when you do indexing like this, array of I, that is just dereferencing array plus I. So an array is just like a pointer in disguise, right? Which is why, oops, I forgot to switch my screen. Yeah, so just look at the code here for a minute. So we have an array, and then we are printing out the array itself as a hexadecimal number, and then we are printing out the array's first element, and then the array's second element, and all of them as pointers, and then we're comparing them between array and array plus 1. If you run this, you can see that array is printing out the same thing as the pointer to the zeroth element of the array, and then array plus 1 is the same thing as array indexed 1, and then we are taking a pointer to that. So that's what I've written here. In general, array of I is the same thing as dereferencing array plus I. So arrays are just pointers in disguise. I hope that covers arrays. And what's next? Okay, realloc and calloc, right? So reallocating memory. Now that before we go to reallocating memory, that's why this worked in the malloc code. If you see here, I've used nums of I. Why does this work? Because arrays are just pointers, one. And secondly, indexing is just a shorthand operator for plus the index whole dereference. So malloc gives you a contiguous chunk of memory, just like an array. So that's why you can use array indexing on malloc memory, right? That's why this works. Okay. Now moving on to reallocating memory. Real. Okay. Let's do include standard. I'm just taking a constant amount of memory here for example. And then we say x of 0 is equal to 1, so 1 is equal to 2, and x of 2 is equal to 3. And say we want more memory. What you would do is realloc and then you would put in the pointer you want to reallocate, x in this case, and then you would say I want more memory or less memory. Let's say I want more memory. What this does is takes your memory and then increases it or decreases it, and then finds a spot to put it and then gives you a new pointer. This new pointer need not be the same as the original pointer. Let's just print out this pointer. %x. Let's print x. Let's say this is the main pointer, and let's say this is also a pointer to an int. And then let's print out session, and then we'll print out x again, right? And then we'll free x because we are good program. Realize. What happened? Okay, we don't need to redefine it. It is yeah. So if we are realloc, okay, here we can see that it's actually the same memory address, but it need not necessarily be the case that is the same memory address. Sometimes the memory address may change. That is completely dependent on how much memory your operating system is currently using, how much free space is available. That's deeper stuff, you'll learn about it later. But basically, realloc need not necessarily give you back the same pointer. It can give you back a different pointer, but the guarantee is the pointer it gives you back will contain the data the original thing had, right? And also, obviously, you should be checking for null in each of these cases. A null would mean an error that it wasn't able to allocate the memory, right? Uh, but I'm just not taking it here for the sake of time. Okay, so that is how realloc works. So you ask for some memory, and then you decide you want more memory. So what realloc does is it just like stacks on more memory here and then gives it to you, right? That's essentially what realloc does. Now what calloc does is it clears out your memory with all zeros. So calloc is essentially the exact same as malloc, except it just zeroes out all the memory allocated. This is in general a good practice because you don't want gibberish data when you have memory. So when you're just iterating over the memory you allocated and didn't write over, you will be guaranteed to get zeros instead of whatever, right? Uh, in some operating systems, it will be zeros by default. In other operating systems, it won't be. That is completely dependent on a platform. To take out that platform dependent factor, you just use calloc. If you want a guarantee that all the allocated memory given to you should be the data held in them should all be zeros or null. Calloc is what you use. Calloc just clears out the memory and then allocates it to you. And then free just you just pass in a pointer and it frees the memory allocated. Just gets rid of it. This tells the operating system I am no longer using this memory. It is not mine anymore. Okay, so that was malloc, calloc, realloc, and free. Any doubts so far? Okay, I assume that there are no doubts. And next, what else? What else? Structures, I guess. Let's create a new file again. So structures. You just say okay. So structures are just the way in which you create a complex data type based on the data types built into C, right? So you can have an integer, a star, or long, or you can even have an array of, right? So all this says is I have a structure foo and it has three things inside. What are those three things? An integer bar, a character badge, and an integer array with five elements false. So that's this what a structure is. So this is how you define a structure and accessing structures. Print main. Let's say struct foo is equal to, let's say the struct foo exists and it is called foo. Now to access something, you would just do dot bar is equal to 1. This is just structure access, right? And then foo dot baz is equal to, and c foo dot false is equal to, let's say 0, right? So now what you're doing is accessing the members of that structure. So you're saying so and so member of the structure should be so and so value. And there's also another way, which is when you have a pointer to a structure. So what happens when you have a pointer to a structure is, let's take an example that initializes foo. Let's say we have a void function. Let's say init foo that takes in a struct foo pointer, and let's call it foo here as well. And then what you'd have to do is you'd have to dereference it and do the dot, right? That's kind of inconvenient. So C has a arrow operator that does this for you. Arrow just means I have a pointer to a structure. So arrow says dereference it and be access a number instead of just doing it yourself. So foo dot bar is the same as access foo dot bar. It's just a convenience operator for your convenience. So let's just do something. Let's say bar is 0, foo dot bar is C, and then we want form 0, 1, 2, 3, 4. Okay, so now we can call this function and then see what it does. And then we can just and then we can print out the members. Say foo dot bar. Person C is foo dot bar, and then this last one I'm just gonna print out like the second pause of 2. Right. So if we compile this, ah, forgot to include printf. Okay, if we compile this now, yeah, I use the dot operator. I'm a dummy. Now, see what uh, Yeah, there you go. So you can see that 2 is 2, 0 bar is 0, bar is C, and then 2.4 is 2. So that's how you write functions for structures basically. You take in a pointer to a structure and then just modify the structure as required or access numbers from it as required. And in general, you should never just write a function that takes in the structure itself because most of the time you don't want to use call by reference when dealing with structures because most of the time you don't want to create a copy of the structure, you just want a pointer to it so you can access it and modify it, right? So that is how you define a structure. And there is also you can also initialize global structures. Let's say I will just say foo here, and if I do that, this will still compile. Now, what foo is a global variable. Foo is a global instance of the struct. I can do foo1 as well, and then I can just printf person b foo1 dot bar. That is also zero because initialized to zero by default, right? So foo and foo1, you can just say how many more things you want there. You can also do type def. You can type def a string and say it is foo. Now when you define an instance, you can just say it is foo of something. You don't have to say it is struct foo. Important to note, when you do a type def, it has to go at the name you are going to refer to. It has to go after the definition. Now, yeah, we don't have a foo one anymore, so yeah, there you go. Right. Oh yeah, I forgot to change the struct here. It's just because we introduced the type def. Now it compiles and we get the same output. So using type def, you can define a type basically. Instead of using it as a structure, you can make the structure behave like a type. So you don't have to say struct name every time. That's also a convenience thing. So that let me just add some comments here. Main point. Right. So that would be structures. What else should we cover? Files. Okay, so file operations. File operations, you just have a few. You can just, alright, so let's just list out all the functions here. So whatever functions you have to take in input or print output to the terminal, there is an equivalent file version. So there is fputs, fgets, fget, f gets c, f printf, f, and then we have f scanf, and so on, right? So what each of these does is, instead of just printing to the terminal, it also takes in a file pointer. How do you get that file pointer? Open files with fopen. So this is how you just open a file. You say I have a file pointer to a file, and then you do fopen. Say it is temp.txt, and then I want to write to it, right? So now what happens is it will be written to. We can use the writing function. Let's say this file and then put a string to it, like hello world, and then let's close. But okay, apparently it's the other way around. That compiled, and then now if we see the content of temp.text, we have hello world there. Say you want to like print stuff, like in text equal to 5, you want to print text to the file. You would do fprintf printf, and then the file first here, and then the data you want to print, just like in printf. There's no difference apart from passing in the file. If we compile that again and run it, you'll see that it's just going to put hello world in there. And then also from fprintf we also have 5. Let's put a new line there for 5. Oh, compile it again and then run it, and then okay. So that is writing to a file and reading from a file. Okay, so this is another case where you might need malloc. When you're reading from a file, you don't know how large the file is. So to read in the entire contents of the file, sometimes you just uh, need to use dynamic memory allocation, right? So we can do uh, let's create a buffer. This bus of 100 bytes. For now, 100 bytes should be enough because we haven't written that much data in that. Now we can just use scanf and then put it all into the buffer, right? Uh, scanf file and then percent s 100. This is me saying there can be only a maximum of 99 characters we can take in, and then the 100th character is going to be none, to indicate the end of the string, right? So int n bytes is equal to that, and then if we just put that into buff, we will have read in the variable, read in the data into the variable, and then we can just do uh, buff of n bytes is equal to 0 as so we are just putting a null terminator at the end of the data that was read in, and then we can just print out buff. And I have to close the file here. Okay, so here scanf scanf is just getting a space after hello comma, and therefore it stops reading into the buffer. So to get any amount of string, we can use fgetS. And fgetS is going to be fget taken buff and the number of characters to read in, which is 100 in this case, and then we can put in the string. But okay, let's take care of the null terminator for us. Yeah, there we go. So f gets read in a single line from here. Say we wanted to just do file operations on the structures or a number or whatever, you would open it in binary mode. There is fread and fwrite for binary operations. Close file, fclose operation, fread and fwrite. So let's just copy over our foo structure. Let's say file is going to be, we are opening another file, temp.bin, and then we are going to write it in binary mode. Now what we can do is use fread and fwrite to store the current state of the structure in a file. So we can say foo, and then we can do foo dot bar is equal to, let's say, 3, and then we can write this to the file. Then we pass in a pointer to food, and then size of food, and then the number of things we're writing. So we're just writing one structure, so it's going to be one, and then we're just going to pass in the file. So this should okay that yeah that compiles, and then it should be created, and okay there is some binary data here, and then if we just open it, fread, let's set foo dot bar back to 0, and then if we read it, the reader operation is also the exact same thing. You just pass in a pointer, and then the size of the thing you want to read in, and then we just pass in how many of the thing. In this case, we're just dealing with one. So now, if we print bar, it should say 3. There you go. It says 3 because we wrote we said foo dot bar is 3, and then wrote that structure to a file, and then load the structure back in the exact same way. So even though we set foo dot bar to 0 here, after that we read in the old state of the structure. So in that file, it's going to be 3 there. So that's how you deal with binary reading and writing, f read and f write. You can just read the syntax here. I'll just comment these later and send it to you guys. And then that's file operations, structs, malloc, realloc, arrays, unions, union, union.c. So what is a union? Union, let's see. Unions are used for uh, storing multiple things, which you only need to access some of it. You would use a one union, which is one use case. And then if you want to deal with different representations of the same thing with clever tricks, you can do that. For example, this is a common union used a lot. So your IP address is going to be uh, let's just check that compiles. Ah, there's no name. Let's fix that. Yeah, there you go. So this is a common example of a union. What's this doing? Unlike a structure, this each member does not have its own space. So both of these things are occupying the exact same space. And in this case, they are both the same size, which you can see often in US, but that need not necessarily be the case. What's happening here is your IP address is being stored as a address, just binary 32-bit integer, or 4 chunks. So this is just going to be like 255 4, 5, 6, 7, 8. Yeah. Yeah. Here it's going to be an array of 4 bytes. So that will be 255, 255, 255, and then 255. Right. That's a quick example. We can just say union before address is equal to, uh, and then we can say that IP dot s address is equal to uh, 1 shift and try 32, 3. That's it. Minus 1. Cast it into a and 50. So that's going to be all ones. Just ignore the minus 1 for now. It will make sense if you think about it. And then if we print out percent %d dot %d dot %d dot %d, you'll get the uh, quote unquote regular variant of the memory 2 and then by 3. Oh, I have to do same bytes 4 is equal to IP dot byte. Okay, I can't do it. IP dot byte, IP dot byte, IP dot byte, IP dot byte. Yeah, 255, 255, 255, 255. So this is an example of a union. So what's happening here is this S address is occupying the same space as this byte. So unions occupy the same space. Each member does not have its own dedicated space. Unions are space efficient ways of storing different representations of the same thing. For example, here the IP address is being stored as a single uh, 32-bit integer as well as 4 8-bit integers, which is what you generally see as like 192.168 dot something dot something. Those are 4 pairs of 8-bit integers. So this is an example of a union. Uh, Again, slightly different from structures. Generally, you don't need to be using them, uh, but this is what it is, and this should be enough amount of knowledge about unions for now. And then what else? Okay, next up, I think we can have covered everything everyone asked for except for recursion. Now, recursion is a little bit tough to approach. So let me just uh, take a simple example. So now let me write a for loop equivalent using recursion to start off with to explain how to approach recursion, right? So let's we have main try plus plus and then we just print I, right? So I'm just going to write this function that does the same thing. It's going to take in an integer. Let's call it I, and then if I is equal to limit return. Otherwise, what we're going to do is print I. Like here, let's just add that, and then we're just printing it. And let's see, we want to advance. So you're just going to call the function again, increase I by 1, and then put the same limit there, right? So let's just compile this. 0, 1, 2, 3, 4. That's what the for loop is printing. Now let's comment that out. And then let's do this instead. 1 and then 5. Sorry, 0 and then 5. Now if we compile it, and it's still printing 0, 1, 2, 3, 4. So this is a simple recursive function that essentially does the same thing as this loop, right? So what is this doing? We're saying if I is equal to limit, we have to return. So this is your base case. So what happens is when you're just going to keep checking until this limit is hit, and until then you're just going to do something to move towards that limit essentially. So here we see that we are just going to print I and then increase I by 1 and then call the same function. This calling the same function is recursive. What is happening? And then you just keep going until you hit the limit. If I is equal to limit, you just return. Now let's look at a more let's say a little bit more uh, Fibonacci in type. Uh, Fibonacci. So this is just going to give us the nth Fibonacci term. So now the Fibonacci sequence is just 0, 1, 1, 2, and so on, right? So if we want the nth Fibonacci term, and we are going to need to start from 0, or we'll start at, okay, let's just do n is equal to 0, return 0. Let's make this unsigned for our sanity. Else if n is equal to 1 or n is equal to 2, we're just going to return 1, right? Otherwise, we are going to return Fibonacci or n minus 1 plus n, right? Let's just, okay, and Fibo. And then we are not void, we are returning an unsigned integer. And then we have a return statement here as well. Oops. Yeah. Okay. This works. Let's say I want to print +md/n and Fibo of 5. Now the fifth Fibonacci number would be 1 plus 2, 3. Let's see if that works. Oh, is it not 3? It's 1, 2, 3, right? Oh, right. Okay. We are indexing from 0. So that's why it's not 3. So 3 plus 2 is equal to 5. Equal to 5 here. Then we fix the 0 indexing problem, and then yeah. So we can actually do for int I is equal to 0, I less than 10, I plus plus. Oh, what happened? What's going on? Yeah, that works. Oh, I'm so dumb. My bad. I less than 10. Yeah. So now I get 0, 1, 1, 2, 3, 5, 8, 13, 21, 34. So we have written a recursive function that gives us the Fibonacci sequence, or rather the nth term in each Fibonacci nth term, and then with which we can generate the Fibonacci sequence, right? So what's happening here? So initially we just call it with 0, it returns with 0. And then when we call it with 1, it returns 1. We call it with 2, it returns 1. And then we call it with 3. What happens? It gives us nth fib of n minus 1 plus nth fib of n minus 2. So it's the Fibonacci sequence is defined like this. It's the sum of the previous two terms, right? So that's what we're taking here. So n minus 1 and n minus 2. So that's going to be what? 3 minus 1 is 2, and then 3 minus 2 is 1. So 1 and 2 respectively. Each of those is going to return 1. So we get 1 plus 1 is equal to 2. And then for the fourth term, we get n minus 1 is equal to 3, and then n minus 2 is equal to 2. For 3, these conditions don't pass, and then it's just going to call this again, and then it's just going to give the same answer for 3 as usual. It's going to be 2, and then 2 plus 3 is going to be 5, and then so on for 8. So this is what recursion is. You're just going to call the same function again and again until you hit a specific base case. In this case, in here, the base case is going to be 0, 1, or 2. It's very important that you ensure that each recursive call you make moves toward the base case and not away from it. So here we see it's an unsigned integer n, and then we subtract. So it's going to get smaller and smaller and smaller, right? So eventually it is going to reach 0, 1, or 2. That is a given. This is very important. If it does not move toward your base case and moves away from it or stays at the same place, then the recursive function will never end and you will end up with a 6xz. We can see that happen if we just comment this out. Now we're not handling the base case at all. So this is just going to recurse forever. And then it just gave us a 6xz because we blew up the stack by doing too many recursive calls, right? So now recursion. Let's understand recursion from a different perspective. Let's understand recursion as return values. Let's say this is your stack. So let's say we call, let's take for recursion first. Let's say we call this with limit 5, right? Limit 5 and this thing is 0. So we are doing 0, 5. So this is going to call itself by incrementing. And then this is going to call increment 3, 5. Then this is also going to call 4, 5. Calling up a bit. And this calls again 5. Now at this point, we have hit the limit. I equals limit. This is true. I is limit. 5, 5, 5 is equal to 5. So at this point, what we are doing is just returning. So when we return, what happens is we go back all the way. So you just call a function, build up, hit the base case, and after you hit the base case, you come back all the way down. So this is what recursion looks like from a stack perspective. Now let's take the Fibonacci case, right? So what happens there? We take a stack. Let's take n is equal to 4. It's going to call with n is equal to 3, and then that's going to call n is equal to 2, and then at n is equal to 2, it will collapse. And table of 4. So now that it has collapsed, it knows we are returning n table of n minus 1, which is 3, minus n table of n minus 2, which is 2, right? So initially this gets evaluated, and this is what this is. You call with argument 3, and then you call with argument 2. N is equal to 2. So we have hit one of the base cases, and then we wind down at each point. At each point, we are returning something, right? So what happens is we wind down one step. After we wind down one step in the 3 call, so here this thing is 3. N is 3. Let's just print that out and give us an example. Of 4. So these are all the recursive calls that are going on. Did I say? Okay, I did not say. Yeah, these are all the recursive calls that are going on. So what's going on here? So from 4 calls 3 first, because there is n fib of n minus 1. 4 calls 3 first, and then 3 calls 2 first, because there is again n fib of n minus 1. So with n is equal to 3, n fib of n minus 1 is 2, and then that returns 1. So we see n becoming 2 here from the print statement, and then it's returning 1. So this is resolved to 1 in the case that n is equal to 3, plus n fib of n minus 2. So 3 minus 2 is 1. So n is equal to 1 now, which we see here. After 2 is done, 2 returns 1. This is done. We are moving on to this part for n is equal to 3. For n is equal to 3, we get 3 minus 2, 1. That is also a base case. We just return 1. This is also resolved to 1. So these both are resolved, and that resolves n minus 1, which is equal to 3 for the initial function called 4. So this and this is resolved for n is equal to 3. So we return, and we are back into the original call of n fib of 4. Now n fib of 4, we have resolved this thing. N minus 1 is 3, and then n fib of n minus 2 is 2. Again, we deal with that base case. We see that recursive call happening here. Now, if we change this to 5, we'll see a little bit more recursion going on. So again, 5, 4, 3, 2. So from 5 it's calling 4. From 4 it's calling 3. From 3 it's calling 2. 2 is a base case. We go back up to 3. From 3 it's going to call n minus 2, which is 1, which is which we see here, 5, 4, 3, 2, 1. And then that resolves n is equal to 3. So we go back to 4. From 4, n minus 1 is 3. That is completely resolved. That returned the value we want. Now we have to find out n minus 2. 4 minus 2 is 2. Again, that is a base case that immediately returns. We can see that call happening here. And after that, we go back to 5 because 4 is also resolved. So from 5, we went to 4 to 3, 2. 2 resolved, so we went back to 3. And that led us to 1. That resolved, so we went back to 4. And then that led us to 2. And that resolved, so 4 is completely done. So we are going back all the way to 5. And from 5, we are jumping to 2 because from to 3. Because n super of n minus 1, 4 is resolved. We want to calculate n super of n minus 2 now. So 5 minus 2, that's 3. We can see that recursive call happening here, and 3 is the same deal. 3 is going to go to 2 for n minus 1 and 1 for n minus 2, and both of them are base cases, and they'll immediately return and not cause any more calls. You can trace out the back and forth arrows here. Let me just do that. Oh, I forgot to change the screen, my bad. You can just look at the code here for a while. I'm just going to draw out the stack here so you guys have an idea. I mean, not the stack, but the way the calls are gonna go, right? And then 3 is gonna call 2, and then 2 is the base case, so it returns. And then we have 3 is going to call 1, and 1 is gonna go back to 3. So this is how a recursive n Fibonacci number call stack looks like. So 5 is going to call 4, 4 is going to call 3, 3 is going to call 2, and then 2 returns. and then 3 is going to call 1, and then 1 returns, and then it returns to 4, and then 4 is going to call all the way down to 2 again, and then 2 is a base case, so it returns. So 4 returns back to 5, and then 5 is going to call 3 because n minus 2, and then 3 is going to call 2, and then it returns, and then 3 is going to call 1, that returns, and then 3 returns. At the very end, 3 also returns. Right. So yeah, this is essentially the recursion going on in action. Any doubts? I guess not. Okay. That's it, guys. If you have any doubts, you can just reach out to me, and bye.